So looking at the display, this is what we're going to see. So the display is basically a digital oscilloscope. So an oscilloscope is the original form of, not TV, but original form of looking at waveform potentials. The original video game Pong was actually first designed on an oscilloscope, as a side note. And what we're looking at here is a sweep speed and a gain. So sweep speed is going to be between 1 and 500 milliseconds per division, and a gain is going to be set. In this next section, spend some time with this. There's a lot of terminology here, a lot of different words that guaranteed you haven't seen before, or if you have, you haven't seen them a lot. Understand just what's happening. Understand that we're measuring the electricity from the cell body down the axon down to the dendrite. That's what we're doing. Notice the green arrow here. Okay, so when we're looking at efferent depolarization, well, this makes a lot of sense, right? We're sending the signal from the brain to a muscle. So what we have to do is we have to appreciate that. And we have to appreciate that orthodronic, in terms of action potential, goes with that depolarization. Now looking at sensory, obviously we're dealing with an afferent. So orthodronic again goes with that depolarization, but now because I'm dealing with an afferent nerve, that depolarization goes back to the brain, goes back to the cell body. So just understand this terminology, understand how each of these work, and don't get too confused and don't get turned around with this. So orthodronic is going to go with the depolarization, antidronic is going to go against it. So taking a look at this study, this would be an antidromic sensory study. Reason is because look at where the stimulator is and look at where the other electrodes are. Think about it. That stimulation is going to go from the stimulator down to the reference electrodes. So it's going to go against the grain in terms of an afferent nerve. So don't let this get you too confused. Just look at where the electrodes are, look at which electrode is where, and look at what we're trying to do. Now this is an orthodromic sensory study. Different setup here, right? So we have our stimulator is more distal, our catcher, if you will, or our reference electrode is more proximal, which is going to mimic how we would expect a sensory nerve or an afferent nerve to run. This slide is simply showing you how the waveform correlates to timing. So if I have a large time between the time I stimulate and the time I catch it, I'm not going to see a big wave. If there's a little bit of time between the time you throw the electric and the time you catch the electric, there's going to be a big wave. So looking at evoked potentials, what we're actually looking at here is a summation of synchronized electroactivity. Okay, remember, use this slide and take a look at the slide we just looked at. So look at not only the amplitude or the size of those waves, but look at how they are formed versus that reference vertical line on the left-hand side of the screen. So looking at evoked potential, what we're looking at here is shape, duration, latency, amplitude, all these things. Area is going to basically mean area under the curve. And usually what's going to be reported is everything except for the shape and everything except for the rise time. Okay, usually we're going to report the rest of those things. So just be aware of how an evoked potential looks and the pieces and parts of those. Specifically, latency is exactly what it says it is. It's the time from stimulation to the onset of the evoked potential. So, for example, I stimulate the muscle, and then how much time does it take for the muscle to respond, and then that's it for latency. So basically it's lag time. I stimulate a muscle, how long does it take from the stimulation to when the muscle actually responds? So there are normal relative values for all of these. They really depend on the muscle that you're testing, and there's obviously reference material based on that. So now the latency for a CMAP is called the motor distal latency, and that's going to be measured from the stimulus artifact, so basically where the stimulus comes from, to the initial deflection, or in other words, where the muscle actually reacts. The latency for a snap is the sensory distal latency. So basically what we're looking at here is if we have a abnormally large latency, what that's really showing is that there is a demyelination in the nerve. So for example, if I zap the nerve and there's a large time between when the zapping occurs and when the nerve actually responds, that's going to indicate an abnormality, which is usually indicative of a demyelinated nerve. Now, amplitude. Obviously, we all know what amplitude means. It represents the sum total of all the fibers in an axon or in a muscle that are recorded. Obviously, there's normal reference values for these as well. Now, a decrease in amplitude is going to mean that there's a loss of axons or there's some sort of blockage, something's not getting through. And usually that threshold's about 50% of normal. So if we get below 50%, we're going to consider that pathologic. Duration and rise time. So what we're looking at here for duration, that's the time required to pass under the recording. So basically the time it takes from get to point A to point B. Rise time is the time between the recording of the fastest fibers and the slowest fibers. And then there's something called temporal dispersion, which is basically a decrease in amplitude and an increase in duration. Don't worry about temporal dispersion too much. The duration and the rise time are much more important. Now the area under the curve is just another representation of the sum total of all the fibers. Decrease is going to mean that there's a loss of axons or loss of blockage. Makes a lot of sense. If there's a decrease in amplitude, there's probably going to be a decrease in area too, right? So why wouldn't they mean the same thing? And what we're looking at here is trying to really look at determining what the true temporal dispersion is with demyelinization, but also realize that sometimes you can have no loss of axons, and sometimes that can lead to this problem as well. So here's your general shapes. So generally what we're looking at is, if we're looking at a CMAP, because we're looking at more of a motor or efferent, it's going to be biphasic. A snap or sensory is either going to be biphasic or triphasic, but usually we're looking at a biphasic as well. So when we talk about nerve conduction velocity, don't get too caught up on the equation at the bottom of the screen. It's pretty darn easy. Basically, it's just a measure of the speed of propagation of an action potential. It is the normal velocity calculation. Meters over seconds, or in this case, millimeters over milliseconds. Looking at motor nerve specifically, what we're looking at is the distal segment of a motor nerve should not be calculated. And the reason is this: the calculation would include the chemical transmission of acetylcholine across a neuromuscular junction. So that's why we use latency, because the latency actually gives us the actual nerve potential as opposed to the time it takes to cook the nerve or times it takes to actually send in the chemicals, and then we have the nerve potential. So what we do is we take the distance between the two stimulation sites, divide that by the difference in latencies, and that's going to give you kind of a true velocity and not velocity with all the extra stuff added in. So looking at schematic here of how nerve conduction velocity is going to occur. So this is going to give you a little bit of a math problem. So pause the slide here, do the math problem. Don't worry too much about the question at the bottom of the screen, but try to do the math problem, and what you should get is you should get an example of nerve conduction velocity. So now we're going to get into more kind of the procedure behind doing a nerve conduction study. Like I've said in the past, please do not take this as entry-level skill. You will have to do a lot of these, and you'll have to do a lot of supervised sessions in order to become board certified in this. Now, looking at all the prep, this is generally the prep you're going to do for any procedure, right? You're going to explain the procedure to the patient. You're going to obviously do a chart review or medical history review. Take a history, make sure you know your subjectives. You're going to check all the potential red flags. Then obviously drape and position the patient. You're going to perform the test, interpret the data, and then write the report. Very similar to every other thing that we do. Now, the specialized stuff you have to do is you have to make sure that your room is sitting right around 77 degrees Fahrenheit, which is a little warmer than a normal room temperature. Reason being is because if we have normal room temperature sitting around 71, 72 degrees, or in my house, 65 if it's the winter, and then 75 if it's summer because I'm a cheapskate, then the reason is if a room's too cold, then we're going to have our fingers and toes get cold first and get cold fast. So you have to actually take the room temperature, and you actually have to take finger temperature and toe temperature as well. So as far as patient age goes, most nerves will mature by about 5 years. Before that, they're just not mature. And we just have to consider that. We will have to do these sometimes on our pediatric patients if we're going to determine something like Duchenne's muscular dystrophy or another pediatric pathology. So you have to take that in consideration, that if you're using this modality on someone under the age of 5, the latency time is not going to be the same. Also, that after the age of 40, there might be a little bit of slowing noted, and definitely after the age of 70, there's significant slowing noted. So, looking at upper extremity and lower extremity usually has a faster velocity. Pretty easy to figure out why. The nerves are shorter, right? They also have a larger diameter of the nerves and thicker myelin, and the temperature is a little higher. Now, looking at proximal versus distal, proximal nerve conduction velocities, and this goes without saying, are going to be a little faster than distal ones. The reason being is because, think back to anatomy class. Think back to how that really thick sciatic nerve branched off and got smaller and smaller and smaller and smaller. Smaller nerve means less myelin, means that we're actually going to have a slower velocity. Couple safety notes here. These are the big safety notes with any sort of electric modality. Don't use it on someone with a pacemaker. You want to make sure that you check first and make sure it's okay. And then if they have metal lines and catheters and anything else that's going to zap them, you don't want to put electricity into something metal, obviously. Now, I've referenced normal values or normative values several different times. These are going to be the normative values. I'm going to be honest with you, I'm not going to test you on this sort of information because this is all easily accessed with references, but just be aware and look at the patterns. So just be aware that as we move down distally, that number changes, and just be aware that those normal values do occur.